A pleasant day to all my fellow conference colleagues. I am Russell Factor from the Department of Mechanical Engineering, University of Santo Tomas, Manila, Philippines. I am the corresponding author of the research entitled Development of a Practical Omnidirectional Germicidal Indoor Carrier Assistant Robot with Line Following Function, with a paper ID of R067. This is the outline of the study. It will give us a glimpse and an overview of the topics covered in this presentation. The first half of the presentation consists of ideas and concepts behind the study, while the second half focuses on the technical aspect of the research. So first off, the statement of the problem. The COVID-19 pandemic has been a major public health problem globally. Frontline workers or medical practitioners are more vulnerable to diseases as they were exposed to their workplaces. Furthermore, indoor spaces where people in close proximity are at high risk of acquiring the disease. In this time of crisis, indoor assistant robots play a role in providing aid to healthcare workers. Thus, the authors have a proposed solution for the aforementioned problems. A mobile robot that can navigate in indoor facilities to carry disinfecting apparatus such as UVC light. As shown in Figure 1 is the 3D CAD model of the overall design idea. This research main objective is to develop an actual full-sized robot with the application of disinfecting indoor spaces. Specifically, this research would like to work on the following: to design and assemble a prototype for the robot base and customize the parameter settings according to its indoor disinfection application. To assess the assembled robot base's navigation performance equipped with mecanum wheels in different testing path plans. Once the authors deliberately assess the prototype through a series of tests and evaluations, the derived concepts and findings can be used for the implementation of an actual disinfection robot equipped with UVC lights. Germicidal indoor assistant robots will benefit commercial establishments in dire need of a thorough disinfection procedure. Thus, the helpful machine will provide a safe working environment for frontline workers. The study's acquired valuable information will benefit the researchers and students interested in pursuing and continuing similar studies. Also, it can potentially inspire and increase the interest of Filipino youth towards robotics. The study focuses on developing an indoor assistant robot that navigates a room autonomously and remotely, with a specific task of disinfection. As part of a more significant effort in developing a service robot to disinfect, the authors only focused on improving the design, automation, controls, and disinfecting feature it can offer to provide a safe working environment by maximizing the use of accessible resources. Due to limiting factors such as COVID-19 pandemic, the authors conducted experimental assessment at the comfort and safety of their homes. The authors did not include testing the effectiveness of the disinfecting properties of UVC light to various disease-causing pathogens. The robot's line follower function will only be limited to a black line and light surfaces to ensure a precise and accurate navigation. This is the graphical representation of the conceptual framework. Together with other parameters, these concepts are considered in the design and development of a mobile robot. A simple hardware, software, and control system was used as a tool for research and study. The base machine used was a four-wheel drive equipped with mecanum wheels as shown in Figure 6 and 7. 3 IR sensors were installed on the front of the robot. These sensors allow the robot to compare black lines on a white surface and vice versa, thus following a line autonomously. The robot can also be controlled manually using an integrated Bluetooth module. The rubberized external rollers attached to the whole circumference of the mecanum wheels angled at 45 degrees provides the robot the capability to move in different directions while maintaining its original position. Table 1 shows the prototype base parts and components. It consists of Arduino Mega 2560, a power source, a Bluetooth module, geared DC motors, driver motors, and IR sensors. On the other hand, Table 2 shows the prototype specifications. The overall weight of the prototype is 0.5 kilograms, max speed of 0.5 meters per second, turning radius is 0, battery capacity is at 3,400 milliamp hour, and the maximum wireless distance transmission is capped at 10 meters. The overall system architecture of the robot prototype is shown in Figure 8. Arduino Mega 2560 serves as the main microcontroller for the comprehensive system that sends PWM commands to the geared DC motors based on sensor signals. 4 independently controlled and driven mechanism wheels were connected to separate ports of the L298N motor driver. These parts operate together to perform a specific function for the prototype to navigate the desired path. The line-following navigation model is shown in Figure 9. Mechanism wheels allow the prototype to navigate effectively in any desired direction. The robot's navigation steering capabilities can be controlled manually using an Android application connected to the HC05 Bluetooth module. The working program diagram of the base prototype following the embedded black line is shown in Figure 10. The IR sensors will first read and detect the black line of the desired path plan. If a black line comes into close proximity of the reflective surface, the microcontroller will send commands to the motor driver to maneuver accordingly with respect to the desirable track pattern. The kinematic model of a four-wheel drive omnidirectional base prototype is shown in Figure 11. The inverse kinematic equations determine each DC motor's required angular velocity to direct the mechanism wheels into desired motion. In contrast, forward kinematic equations will locate the base prototype's path from the motor's rotational speed. The authors use the acquired values from these derived equations in coding and programming the microcontroller. For the navigation performance of the prototype, the authors created various track patterns. The first path consists of 30 degrees of turns. For the second, it consists of 45 degrees of turns. And the third path consists of 90 degrees of turns. The difficulty levels were categorized as easy, medium, and hard. The authors tested the prototype robot's navigation capabilities in a pre-planned course to ensure that it can perform effectively in much more demanding tasks, as shown in Figure 13. The average total distance traveled by the robot is 5 meters. Tables 3, 4, and 5 show the data gathered from the test performed. The authors considered constant speed setting with a duty cycle of 50. The robot prototype followed embedded black lines on the floor smoothly and faster than manually controlling it. The tendency to astray from the line was ranked from low to high. It demonstrates that the robot still requires further decoding and calibration in preparation for a much demanding path in the closed-loop test. After the initial testing, precise fine-tuning and calibration were done to the prototype. The subsequent performance assessment is done through a closed-loop test, where the prototype must overcome a much demanding path plan as shown in Figure 14. The results of the closed-loop test is shown in Table 6. The robot was successful in navigating from starting point to finish. The test only focuses on the line follower function because it executes the command with precision and accuracy. It also follows the line without any delays in comparison with a remote-controlled function. The results and analysis of the data gathered will be used to design and fabricate the actual service robot model. A full-sized robot, named as the LISA or Logistic Indoor Service Assistant Robot, was developed after a series of successful performance evaluation of the prototype. The LISA robot was used during the first surge of the COVID-19 pandemic and was tested in different office facilities and corridors of the University of Santo Tomas, Manila, Philippines, as demonstrated in video number 2. It was designed to carry disinfecting UVC light and navigate around an empty room by following a black line embedded in the floor. The LISA robot can also be controlled remotely using a Bluetooth controller. 4 independently driven mechanism wheels were installed to allow the LISA robot to maneuver in tight locations. The author successfully developed and assessed a base prototype of an omnidirectional, germicidal, indoor carrier assistant robot with the line following function. The authors tested the prototype's navigation performance on various track patterns and a demanding path in the closed-loop test. In designing a course for the robot to navigate, 30 to 45-degree angle of turns must be considered to ensure a smooth and precise line tracking of the robot. Thus, the results and observations highlight specific areas of improvement to perform proper calibration and accurate fine-tuning. The authors used the concepts derived from the prototype to design a full-sized Lisa robot. It was able to navigate in indoor facilities carrying disinfecting apparatus such as UVC lights. This is the end of my presentation and thank you for listening.